So the last part of today's notes is based on something called improper integrals. And essentially it's calculating the area under curves where the curve is unbounded. So there are some ways we can have curves unbounded. So improper integrals or unbounded integrals happen when the curve is along an asymptote. So this is unbounded because as the curve goes up, it goes up to infinity, so we can't really actually reach infinity, so this is unbounded on this side. A curve can also be unbounded on if the x values go out to infinity, because we cannot actually close off this curve, so it goes off forever to infinity, and again we have an unbounded situation here. So those are two essentially two ways we can generate unbounded integrals or improper integrals. So when we're integrating, we have to be careful not to integrate across asymptotes, and we have to be mindful when we integrate to infinity, we're dealing with an improper integral. Now, we can integrate these without limits, but to really do it properly, we really should use a limit because we are going to infinity. And the y value is going to, or sorry, the x value is going to an asymptote. Again, we can't actually get to the asymptote, so we really should be using a limit in these cases. Now, it works without the limit, but again, formally, we should do it with a limit. So when we're integrating, we have to be careful. We have to look for these unbounded regions, or one of the easy ways to find them is if we're integrating across vertical asymptotes. Okay, when we see our bounds cross an asymptote, we really need to split that up into two pieces of unbounded integrals. Otherwise, we get really weird results. We get results and they appear valid but are invalid because we've gone across an asymptote. Now on the bottom here, this is just a guideline. You don't really need to know this, but it's a good guideline to know. So if you have 1 over x function where n is less than 1, or sorry, in this case be kind of greater than 1, or the n value, the negative n is less than negative 1. So an example would be something like this, 1 over x squared. Oh, sorry, this is, yeah, so this is when n is, we are talking, when this 1 over x squared, what ends up happening is it dives down to 0 very quickly and it pinches off there and we end up with finite area on this side. Now the nice thing is, if it's finite on one side, so if this is the same curve, 1 over x squared here, on the other side that is now bounded by the asymptote, this is an infinite area. It's the opposite. So here we're going to infinity. This area under here ends up being finite. Well, the opposite occurs here. And vice versa, the converse happens when we have these powers that are less than 1 in the denominator. So I'll give you an example here. This one would be like 1 over root x. 1 over root x does not dive down to 0 as quickly as 1 over x squared. So this area gets a little bit bigger, and that little bit extra area makes it infinite. And just like with the other example I gave you, if this was 1 over root x, if this curve is 1 over root x, if it's infinite on one side, it's finite on the other. So when we bound this not to infinity but along the asymptote, this area, unbounded area, tends to be, or it is, finite. Okay, so we can actually calculate a value. It's not infinite area. Okay, so these are kind of some good guidelines to know. You really don't need to know this for this course, but once we get into the second part of calculus, this is very useful to know. So I'll give you some examples of how we can set this up. Okay, so an example here is we have our 1 over x function. Okay, and there is an area, so I'm gonna do the first area in red, this area here. This is from 0 to 1. Okay, and then on the other side of that, this is from 1 to infinity. Okay, so that would be that area here. Okay, and this curve, which I'll do in black, that curve is y equals 1 over x. Now this is special, this function is special because this happens to be the boundary function, and that property that I just gave you where if it's finite on one side it's infinite on the other and vice versa, it actually doesn't apply here because this is a boundary one where this happens to be infinite on both sides. Now I'll show you how to apply the limit to calculate this improper integral though. So when we do actually calculate the area, so the area is going to be the limit as x goes to 0, okay, because we can't actually get to 0 of, oops, sorry, I'm going to need to use a different variable here. I'm going to call that a, as a goes to 0 from a to 1 of 1 over x dx. So that's how I'm going to set up that integral. And the limit notation really is just kind of formal. If we don't have it there, we'll get the same result. So if I anti-differentiate this, okay, I'm going to run out of space here, so I'm going to have to do it over here. If I anti-differentiate this, this is a limit as a goes to 0, and this is going to be the log function, log x from a to 1. Okay, and then I can now calculate this. I can plug it in. So when I plug this in, I get log 1, which is 0, minus log of 0, which is negative infinity. Okay, and we're approaching it from, oops, sorry, I should say we're approaching it from the positive side. Okay, this is approaching from the positive side. So as the log function goes to 0, it's going to infinity. So we end up with, negative infinity. So we get 0 minus negative infinity. So that area is infinite. Okay, so that red area is infinite. And so that is, first of all, the area is infinite. And this is how we set up our improper integral when we're integrating along and up to the asymptote. Essentially, we just use a limit so that we can actually get to that 0. And then same thing on the other side there. If I'm going to calculate that blue area is going to be the limit as a goes to infinity of 1 to a of 1 over x dx. Okay, and then I will anti-differentiate that. We get log x from 1 to a. So this works out to be log infinity, which is infinity, minus log 1, which is 0. So we end up with an infinite area. Okay, so this is how we set up an improper integral. It's when we integrate up to the asymptote, or if we integrate out to infinity. Essentially, we need to set up a limit to do this. And this function that we just did happens to be a boundary function, and we look at this later on, but it is a boundary function in that it is infinite going this way and infinite going this way, where all the other reciprocal functions are finite on one side versus infinite on the other side. And again, that's something that you don't need to know, but it's nice to know.